Good afternoon, everyone. Welcome to Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and RBC CPS IAC. It's my pleasure to introduce today's speaker, Professor Andres Kwasinski. He will be speaking on the synergy between quality experience and deep reinforcement learning for uncoordinated multi-agent resource allocation in cognitive radio network. He is a professor and director of the PhD program in electrical and computer engineering at the Rochester Institute of Technology, USA. He has co-authored more than 110 peer-reviewed publications and 4 books published by Cambridge University Press and widely. His research interests include cognitive radios and wireless networks, cross-layer techniques in wireless communications, and smart infrastructure and networking. He currently serves on the senior editorial board of the IEEE Signal Processing magazine, where he has also been area editor and associate editor. He has previously served as an editor for IEEE Transactions on Wireless Communications and IEEE Wireless Communication Letters. He received a diploma in electrical engineering from the Buenos Aires Institute of Technology, Argentina, and MSc and PhD degrees in electrical and computer engineering from the University of Maryland, College Park, USA. He is a senior member of the IEEE. Over to you, Professor.
Okay, thank you very much. So, yeah, first, thank you for the introduction, and also thank you for the invitation to present here and to share some of my research work with you. As I go through the presentation, of course, feel free to stop with questions if you see there are some things that I need to explain better or discuss more. But let's get into it. So today what I'm going to be doing is first I'm going to explain you what is the environment, the setup of the problem that we are going to be looking at, which has to do with the spectrum sharing, and what is the solution that we are going to be using, deep Q learning, why and how we are using that. But most importantly, then we are going to be discussing some issues and solutions to these issues that happens because of these decisions that we are making to solve the problem. We are going to be looking at how to learn faster in this deep Q learning solution. And all through this, we are going to see the important role that mean opinion score as a measure of quality of experience has. Then we are going to talk discussion, and I have at the very end 4 slides for more general discussion, like a bonus material that I will also will presenting to you. This work, I want to acknowledge my student, my former student, Fatima Shah Mohammadi, which did a good part of this work. All right. So, as I said a moment ago, this problem is a problem, I mean, the problem we are looking at is a problem of spectrum sharing. And more specifically, what we are going to be doing is doing a spectrum sharing in what is called underlay dynamic spectrum access. What is underlay dynamic spectrum access? What is it? Spectrum. In this paradigm, we have 2 networks that are coexisting and using the same portion of the radio spectrum. Okay, there is one primary network that is what we call the incumbent, the owner of that portion of the spectrum. Essentially, is the one that is paying to use that portion of the spectrum, and so it's entitled to receive the service, to enjoy the service that that portion of the spectrum has, right? So that is what we call the primary network. And then we have a secondary network that is going to be using the same portion of the spectrum, but in a way that is not affecting the service that the primary network is receiving, okay? So from the perspective of the primary network, this secondary network is practically non-existing, okay? So how we do that? Well, we impose a condition on the transmission of this secondary network, that is, all the nodes in this secondary network need to transmit with some power that the interference they create on the primary network is below a certain limit, okay? So the interference that this secondary network is creating on the primary stays below a limit that is set so the primary network do not feel that there is some other network operating in the same spectrum band, okay? We are in this talk today, we are not really looking much of what happens with the primary network. It's really, I mean, it can be a dumb network for all what we care about. The one that we are really caring about is a secondary network, and there is what we are going to have what we call secondary users, and really the term I'm going to be using in cognitive radios, right? And I'm going to mention why we call them cognitive radios, okay? Again, the diagram here is emphasizing that idea that the secondary network, the cognitive radios, are going to be transmitting with a power such that it stays below an interference limit on the primary network, okay? Well, a little bit more about these cognitive radios, the secondary network. Well, they are, of course, they are going to be establishing links between each other. They are going to be transmitting, again, subject to this limit on the interference on the primary network. There's going to be other requirements in how they are going to be transmitting, and notably, that, of course, that the quality of their transmission, the transmit power, and so on, that they achieve, have to meet some quality of experience requirements. We are going to talk more about that, okay? But essentially, that will translate those requirements of quality of experience will also translate into a target signal to interference plus noise ratio, SINR, for those cognitive radio links, okay? Something that I'm not going to have the time to get too much in discussing, is something fairly simple also to go through, it just takes time, is that as we are going to be looking at how these cognitive radios do essentially resource allocation each other, well, they are going to be using, as is common today, in their transmission, what is called link adaptation. That is, they can choose the best modulation scheme to transmit. They can choose also the coding, the channel coding that they want to use, right? I mean, and they choose that so they have the best link, right? When they are transmitting. Well, those choices, you know, modulation and coding and transmit power that goes with that, essentially adjusting transmit power and rate, is equivalent actually to just find what is the SINR, the target SINR that they need to be meeting in their transmission, okay? So again, I mean, this is something that we are not going to get the time to look too much in detail, but it's something fairly simple. The point is that, so you understand what is going to happen later when these cognitive radios are going to be finding their, I mean, they're going to be doing resource allocation. In practice, the way they're going to be doing is trying to find the best SINR for the link, for their link, okay? Something also to mention, well, actually that will come later, so I'm not going to jump ahead. I mean, it's actually here. Well, how we are going to implement this, okay? And the way that these cognitive radios are going to be operating and making this, finding this best SINR, target SINR for them to operate, is using a deep Q-learning paradigm, a deep Q-learning solution, okay? Why we are going, I mean, essentially deep Q-learning is an implementation, is a modern implementation of reinforcement learning, right? Why we do that? Well, I mean, the simple ways to do that, to say that, is because it's a natural fit to the problem, okay? To the problem of a cognitive radio learning by itself to find, to understand the environment, right? Because we are assuming that these cognitive radios really do not know much about the environment. They need to learn how this environment is, a wireless environment, right? Interference, both to the primary and from other cognitive radios. They need to learn all of that, right? So we can essentially find a solution using this model-free approach that is part of this deep Q-learning. And also the way this works is following this idea of what is called the observe, orient, decide, act framework, okay? This is essentially a description also of how the deep Q-learning works, but it's also, in a way, I mean, it is the reason why I'm calling these cognitive radios, okay? If you look at research out there today, you are seeing less and less mentions to the word of cognitive radio, and that is a bit because of, you know, how things have been going. People today more and more are talking about machine learning applied to wireless communications, right? And this is a case of that. I mean, I could also be saying this is machine learning applied to wireless network, But I chose to emphasize still the use of cognitive radio because I wanted to emphasize this type of operation, right? I mean, and this type of operation is essentially how reinforcement learning works, okay? That is, it's a cycle essentially of trial and error, right? I mean, during a sequence of learning steps, in each learning step, the cognitive radio will choose an action to do, and this action again is essentially is finding the transmit rate, the power allocation, but again all of these get packaged into just finding what is the best target, the target SINR, right? So the action is finding a target SINR. That again gets translated into transmit power, bit rate, and so on. But the thing is that in this deep Q learning, or this cycle of observe, orient, decide, act framework, the cognitive radio will choose one action, will try that action, and will measure what happened, both with environment, how the environment changes states, and also it will measure, will sample a reward out of that, okay? A reward is essentially a measure of the fitness of that, the result of that action in terms of a goal that we wanted to achieve, okay? The goal in this case, broadly speaking, that we want to achieve, and I'm going to detail more later on why, but I mean, broadly speaking, the goal here is to maximize the quality of experience for each link, for each cognitive radio, okay? Something I want to emphasize, because it's also part of the problem here, is when each cognitive radio, each of these deep Q learning agents are trying one action on the environment, each they are operating without coordination, okay? Each of these cognitive radios operate without coordination, okay? And what is the important, why is that is important? Because there is no coordination, the observations of the reward that the different cognitive radios are going to see, they are going to be noisy, okay? Noisy because different, as one cognitive radio is taking one action, other cognitive radios are also taking action with their own actions without coordination, right? And so what is a reward that is measured at one particular time for one action and one state with some value, a few moments later, taking the same action with the same state may receive a different value with noise, right? Because other cognitive radios were taking different actions, right? So that makes the learning, okay, I should maybe take one step back. So what happens is then through this process of is that me? No, okay. So what happens is that through this process of taking actions and measuring the reward, the cognitive radios gradually start to develop essentially an understanding, a representation of the environment, okay? How is this the environment represented is through what are the Q values, okay? The Q values is essentially an estimate of the cumulative, of the expected cumulative rewards that is obtained when taking one action in one particular state, okay? And the other way that you can think of the Q values, this is useful for what we are going to see in a moment, is that this is a variable of two, sorry, it's a function of two variables, okay? The two variables for this function are state and action, okay? Yes, you have a question. Yes.
What do you mean by, I could not follow what are the actions there and what are the possible outcomes there? Is it like a multiple lines there?
Yeah, that's a good question. So the question is, what are the actions that are being tried, right? So it is essentially a set of possible choices for target SINR on the transmission, okay? So that are different choices. Now that choice of target SINR is translated into a transmit power and a transmit bit rate. And also that transmit bit rate is translated into modulation and channel coding, okay? Choices of all that. So, I mean, it's much simpler to look at this problem from the perspective of target SINR rather than what is the other triplet of value I just told you. But in reality, that is what is happening.
Okay, and is there any drawback if
two CRs will collide?
Well, yes. So what happens is when that happens, so it may be the scenario where the two chooses as action something that translates into high transmit power, right? And then in that case, interference to each other is going to be too large, right? So what is going to happen in that case is that the reward that is going to be measured is going to be low. It's going to be low, right? And so that is a scenario. I mean, there are all possible combinations of what may be happening, right? And through this process of trying different actions and seeing what is the reward is how the cognitive radios start to build an understanding of what is the environment, right? A representation of the environment. Thinking of the environment as or the representation of the environment of what are the different states in the wireless environment, and what are the best actions or worst actions for each of the states. Okay. Yes.
So, like, how do we not know that a deadlock-like scenario won't happen? Like, if two agents are two agents are trying to improve their own situation, they might enter a state where they're working against each other.
Yeah. So that question goes into something that is really not really mentioned here, but is just this word here, do an action, right? But the question that the question that you are asking is essentially the implication is how is that we choose those actions, okay? And as I said earlier, what happens here is a process of trial and error, okay? There are different actions that can be taken, okay? And initially, so this is going to take several learning steps to get to learn what is the best action. So initially, what happens is in what's called an exploration phase is that the cognitive radios chooses multiple actions, different actions almost at random. One moment they choose one action, then the other moment they choose a complete different action, okay? So essentially I'm trying to get a broad idea of what is the environment, right? Essentially a broad look at these Q values, essentially, right? As they keep doing this, eventually these Q values are being estimated, right? And the goal here is to find, remember, Q values are a function of two variables, action and state, right? Are to find the Q values that for each state what is the action that for each state gives you the largest Q value, okay? So as the learning progresses, there is a transition from randomly choosing actions into trying more and essentially improving your estimate for those actions that are giving you the best rewards, okay? Now, there may be situations where maybe two of these cognitive radios are too close to each other that maybe there's no action that they can take that has a feasible solution for what is the quality of experience they want to have, right? And in that case, well, they will realize they're going to learn maybe I cannot transmit now, okay? It is not common to happen, but potentially, there's always a probability of that for that to happen, you know. And they will have to learn that is a solution, right? Not a good one, but they will have to learn that is a solution, you know.
Also, is it possible to simulate, get a digital version of the environment, and then rather than having it as uncoordinated agents, make them all coordinated and learn the optimal policy for each agent?
In a coordinated way, in a centralized way, it is possible. In other sub-problems, so we are going to be talking about one particular sub-problem of this today, but in other sub-problems, actually we do that trick as a way of finding a global optimal solution to the problem, right? In this case, they are equilibrium states. They are not, because this is kind of like a game setup what we are having here. But in some other sub-problems, what we are interested is to see convergence to a global optimal. And in that case, we do what you are talking about. Artificially, we create like a genie that can, know everything, and then it can do that.
But is it not possible? Like, suppose this is my environment. Everything is fixed. But is it not possible for me to simulate it?
Well, okay, as a simulation. Yes. Well, it is. Yeah, it is a different approach. Okay. I cannot get too much into that. I mean, it takes a whole other presentation, right? But there are variations. So deep learning is one way of implementing reinforcement learning. Today there are many other ways of doing that, PPO and many other ones. There is some work, not by me, but other groups that are using even attention mechanisms. And they use attention mechanisms to what is called action critic type of schemes to separate essentially evaluation of the reward versus what action to take, right? One of those two things are then centralized, okay? Is done in a centralized way. So there are solutions. I mean, the quick answer is yes, it can be done, and there is different type of work where that is being done, yes. All right. So a couple of things, I guess two things that are left here to say is that the final goal here is to identify what is the best policy. That's the word we use. A policy is essentially a mapping from a state to action. Okay, so knowing what is the state, what is the action I should take. Okay, and as I said earlier, that action is the one that provides me the best quality of experience. I have been talking about quality of experience. In a moment, I'm going to explain what I mean by that. Okay, and again, I mean, this is what I just described here. For the most part, is all what I describe is reinforcement learning in general. Okay. Specifically, deep Q learning, what we do is we use a neural network to essentially do an estimate, a regression of what is this Q value function. Okay, that's all what it is. Okay, we use neural networks just to estimate what are these values by sampling. Again, through this process of taking an action, seeing the change of the state, measuring a reward, and then continue doing that in the process of estimation. All right, so that was one element of the problem, right? The element of how we are going to be implementing this from an algorithmic perspective using deep Q learning. Now, transitioning into another element of the problem, I want to talk about resource management and what are, how modern resource management is today, right? And why I emphasize modern is because I want to talk a little bit of what has happened with 5G. 5G is the first cellular standard that actually has been designed specifically to support different type of traffic. There is what is called ultra reliable and low latency communication, which the name kind of tells you what it is, right? There is also enhanced mobile broadband that is the evolution from what is LTE, right? I mean, to have video streaming and that kind of services. And then there is massive machine type communication, which essentially is IoT devices, right? Each of these type of traffics are very different from each other in what are their requirements, on how they work, and very, very different. Even within enhanced mobile broadband, even within that class, still there are many type of traffic that are there. There is web browsing in there. There is check email, but there is also video streaming, very different, each one from each other. And the problem, I mean, always, but it has become even more of a challenge, is how is that we can do all this resource management when in the same system, right, in the same network, when we have such a different service requirements for the different type of traffic. So that is one part. The other part is also related to 5G. There has been really transition from the traditional way of doing resource allocation into now emphasizing what is called end-to-end resource management. Okay, and what that means is really is looking. We still look at what happens in the network, but now we've become really interested and we really emphasize what the end user is experiencing. Okay. Oh. So, what does this mean from the perspective of our problem? is that in the traditional way of working with this, of doing resource allocation and measuring also the performance, the traffic performance on the network, it was based on quality of service. Okay. Today you hear maybe as many times people are out talking quality of service or talking about service KPIs, key performance indicators. I mean, they all are referring to the same thing. They are objective metrics, and you see I'm emphasizing that, of how that individual links are performing. So measuring bit error rate, right? Bit or packet channel packet error rate, or the bit rate that we are transmitting, delay, right? These are things that we can measure. These are objectives, objective measurements, right? Because we have a number that we are measuring. Now, with the end user centered approach that I mentioned that we are transitioning more and more into, thinking about the end user perspective means that we are now looking at quality of experience, right? And what is this quality of experience? To use metrics that measure performance from a perceptual point of view, okay, from a subjective point of view, okay, is essentially, take video streaming, right? How delay, how error rate affects our opinion of the service. Are we going to say that that service is excellent, poor, fair, right? Of course, all this, the quality of experience, this perceptual or subjective measurement are related to what happens with the quality of service measures, right? As I'm saying, I mean, if we experience a lot of delay, we are not going to like that service. If the delay is very fast, we are going to like it, right? So what has happened is that over the past couple of decades, there has been a lot of work of, and also on the interest of making this practical over live networks, of how we can use quality of service measurements to assess what is the quality of experience that we are we will be measuring, right? The point is that we can measure through on a network bit error rate, bit rate, delay, and from there we can say, well, these numbers correspond to a fair quality of service, a quality of experience, or correspond to an excellent quality of experience. Okay. In many cases, this is done through an algorithm. I mean, there has been research that has developed these algorithms. Some of these algorithms are even standardized on ITU, for example, especially on the side of speech and things like that. So one of the, I mean, there are different ways that we can measure quality of experience, but the one that really we care about here is mean opinion score. Okay, mean opinion score is a metric that it measures, your quality of experience in a scale from 1 to 5. Okay, 1 being bad quality, 5 being excellent. You see there the chart. Why is it called mean opinion score? Because it goes all the way back, 50, 70, 80 years ago with old telephone networks. And when there was some improvement, something that they were done on the telephone network with research, AT&T or other of the big research labs will get in a room a panel of people, right, human subjects, and they will play, one option, another option of whatever they were developing, and they will ask that human subjects, tell me what you think. Do you think this is good, this is fair, this is poor? Give me one number between 1 and 5, okay, for that. And that is what was called the mean opinion score. It's actually also a standard in ITU, again, I don't know how many years ago, 70 years probably, or even more. But the idea is that now we move into the digital age, and what people have been doing is to try to get a measure of mean opinion score from just measuring objective metrics, without the need to get people into a room and say, what do you think about this, okay? So by measuring, again, bit error rate, delay, and so on, from a live traffic on whatever is a type of traffic, video streaming, for example, to get an assessment of what is the mean opinion score for that. And these are algorithms, and it's essentially using psycho-perception theory and things like that, right? That exists out there. Now, what is important is when what we have today is kind of like a library of algorithms for different type of traffic that all converts all these objective quality of service measurements into mean opinion scores measurements, okay? And what is important there is that then what we are doing is measuring the quality of experience, or just broadly speaking, the quality of whatever is of those services, regardless of how the service is. We are using always the same scale, okay? Always the same scale for all those type of services. All right. So here you have a couple of examples. The two examples that we are going to be actually centering, looking at in this talk. Data, specifically FTP, the mean opinion score, how you can calculate that. And this is one where the mean opinion, the FTP, you care more about bit error rate. You don't care so much about delay. Video mean opinion score. See, the objective measure here is PSNR, peak signal to noise ratio, which is measuring the effects of video compression, okay? But through perceptual studies, people have found a way of measuring on correlating that with mean opinion score. And there is one other element, that is the delay, that we are going to be introducing in the next slide, okay? So, how is this connected to what I was talking earlier about deep Q learning? Well, calculating the reward. Okay, remember the reward is a measure of the fitness of the action result to our goal, and our goal is to find the action that gives me the best quality of experience. Okay, so essentially what we are going to do is to design our reward to be measuring quality of experience. That's essentially what we are doing, and the way that we do that is by having that reward being a mix between that quality mean opinion score that we just mentioned plus an element of delay. Okay. Now, as I mentioned a moment ago, FTP, we don't care that much about delay. Okay, we really care about bit rate. And so, when we are talking here about delay, really we are having an element of penalty or reward for what is the video streaming traffic. Penalty if the delay is more than, say, 140 milliseconds, right? Then that becomes a negative reward, right? It's a penalty. If we have less than 100 milliseconds, it's a reward, right? These days we are experiencing, with Zoom, the interactive video communication, right? So you get an idea. Things becomes annoying in terms of delay if you start to have delay about, well, the number that you have here, but just a rough number, 150 milliseconds is when we start to talk over each other, trying to coordinate that communication, right? And that's why you see this penalty here with the delay, okay? But you see here the reward is calculated in this way. When everything is fine from the perspective of, going back to the earlier part of the conversation in terms of interference, right? When the interference of the primary is correct and all that. If the interference to the primary is violated, then we are having a constant number there. Is a big negative constant as a penalty for what we are doing. All right. So when we are talking about reinforcement learning, we need to define three things: reward, action space, which is a question that you asked me earlier, and the state space. Actually, I already answered the question about what is the action space. These are target SINR. Okay, that's kind of the answer to that. The state space in this case is a triplet. There is one element of the triplet that is, we give the state, we call it 0 or 1. 0 if the SINR constraint on the primary network is satisfied. The other element of that state is 0 or 1 also, but now looking at the SINR on the secondary network. And then there is one last element that has to do with measuring the delay. Okay, there is a delay requirement, right? And it is 0 if everything is correct. It is 1 if we have too much delay. Again, here with data traffic, FTP, we don't care that much about that, so all the time is going to be equal to 0. All the time is fine. Okay, that's what we are saying. Yes?
How do you know the first one? So do you assume
Oh, that's a very good question, but this is another presentation. That's another application of machine learning in wireless communications using, in this case, not an estimator like we are doing here, but a classifier. If you and you take advantage of that the primary network is also using link adaptation. It's changing modulation, it's changing channel coding rate. And so essentially you can train a classifier to work in this way. The cognitive radio may be sending a few sequence of a few probe messages at different transmit power, and then measure what happens on the closest primary link, and estimate what is, or measure what is the change in modulation that is happening on the primary link. And through that, essentially a supervised training of that classifier, learn what is the interference that you are creating on the primary link. Okay. Yeah. All right. This is now a picture of how everything works. I mean, going back to that picture of how the system works. And here, essentially, you see the deep Q learning implementation. I mean, we don't need to get into all the details because it will take too long to get into that. But really, the emphasis here is that this is done again through a neural network. Okay. Of course, we train the neural network through a backpropagation with a cost function. In this cost function here is trying to minimize the mean square error between what is our estimate of the Q values to what we are measuring in terms of rewards with each learning step. Okay. All right, and so what is? I mean, we put this to work, and what is that we see? Well, we see that the thing it works. Okay. We see how these cognitive engines in the cognitive radios essentially learn how they can transmit, right? And we can measure the mean opinion score. Here, what is going to be of interest to look at is as a function of the number of active links in the secondary network. So essentially, how many pairs transmit-receive pairs we have on the cognitive radios. Okay. Of course, the more that we have, we are not changing the size of our playground, so we have interference is increasing. We may get to what you were asking earlier, right? Two cognitive radios being too close together, right? So that's why you see how the mean opinion score is decreasing as we have more transmit-receive pairs, right? Because there are more interference between them. Now, drawback of what we see, the problem is that it takes too long to learn, right? You see the numbers, and this is essentially how much time, how many training steps, how many learning steps we need to go through to learn. Okay, so what we can do about that? Well, what we can do is first we take a pause, and we look at how these Q values look like. Okay, the Q values is again the internal representation of that environment, and the rewards that we get at different states for different actions. So what you see here on the left is a plot where you are seeing the mean relative difference between the Q values between two cognitive radios that are at different distances. We are moving the distance. We are separating them apart more and more, and this is the distance. Basically, the message of this fancy plot is that when the closer they are, these cognitive radios, the most similar is their internal representation as a Q values. Okay, the representation of the environment is most similar. Similar thing we can see if we look at the weights. Okay, the implementation that we have here is a three layer. And if we look at the weights, we see that the closer they are, the more similar the weights are. Okay, so this is natural in the sense that the closer the two cognitive radios are, their environment gets to be more similar. Okay. All right, so then the scenario is the following. So we have a scenario where a cognitive radio now joins the network, right? We turn it on, and it's time to establish a link, right? And so really because of this observation that we just made on how it is similar, the Q values, well, what we can say is that there's no need for this new coming cognitive radio to start learning from scratch, okay? In principle, what we can do is if the other cognitive radios that are in the network already and they have gone through the lengthy process of learning, if they can transfer their experience to this new coming cognitive radio, well, that will speed up learning, okay? They are not starting to learn from scratch, okay? Yes, I mean, after that transfer happened, there will be a need to keep learning and fine-tuning that learning, but we don't need to start from scratch. Which one are we going to choose as that other cognitive radio that is already on the network and is going to transfer the experience? Well, that we see from these two plots, but most clearly here, as I said, the closer we get, the more similar are these Q values, right? The internal representation. So what we can do is to choose as that more experienced source of the experience, right? The closest cognitive radio to the one that is just joining the network, okay? So, again, I mean, the kind of repeating the idea here, now using the thinking of a teacher and a student, right? So, the new cognitive radio is going to be the student. The other cognitive radio already there is going to be the teacher. And so that teacher is going to transfer the experience to the student. The student will have to follow a little bit still of learning, okay? Because it's not perfect match. The internal representations are not identical. They are more similar the closer they are together, but to each other, but they are not identical. So it will be a last stage of fine-tuning that learning. All right, and so how is that is done in practice? So first, I mean, again, the repetition of who is going to be that teacher is the nearest cognitive radio that already have learned. So the closest one to that there, so you can see that. Sorry, where the cross correlation is the largest, right? So it's where you have a highest coincidence between the student and the teacher, essentially. Okay, and what we can see is that, well, with this transfer learning, there is a little bit of a decrease, but very, very minor on the mean opinion score. By the way, we want the mean opinion score to stay above 3. Okay, that means that nobody will be complaining, essentially, of what is subjective quality. And so that is, again, there's not really much of a loss in terms of mean opinion score, of quality of experience, but what there is a big, big increase, gain in learning speed. Okay, this is the one, the black line is what we had before, no teacher, no student, and here what we have now. And you see that there is no also difference in that speed if you are transferring all the weights or if you are just transferring the last layer. All right. So as a summary, here we talk about our conclusions, right? The conclusion of this work, we talk about this learning in this underlying dynamic spectrum access sharing environment, where the network supports, the cognitive radio network supports multiple types of traffic. We talk video and data, but this can be also, of course, generalized to other type of traffic. And we use reinforcement learning because of the natural fit for that. And we use the reward using mean opinion score to measure end-to-end quality of experience approach, right? The important here is that we use mean opinion score. It gives us the same scale we are measuring with a common scale for all traffic types, okay? So how we talk about how we learn faster is by having this teacher that is experienced cognitive radio closest to the new cognitive radio that is the student, right? What is really important here is to see, to observe that parameter, that transfer of the parameters is agnostic to the traffic type. Why? Because again, designing the reward, the measure of fitness, using the mean opinion score that is the same scale for all traffic types, okay? So we got 80% faster learning, okay? And if we only transfer the last layer, we have 90% reduction in overhead, right, on what we are transmitting. So of course we do that, okay? So with that, we conclude the part of the technical part of the talk, okay? And as I mentioned earlier, it's a little bit of a bonus I wanted to talk to you about, because it's something that is really what occupies a lot of my time today. Something I thought of spending the last minutes of the presentation today talking, because I thought it was also of benefit for, talking about in general, right? And so what occupies a lot of my time today is that I am, as you mentioned in the introduction, I am the director of a PhD in electrical and computer engineering back in RIT. And to that comes that really, what my job is to form an ecosystem where we form the best researchers that our students could be, right? Elite researchers. And as part of that, I teach a course on research methods, right? So, this is essentially an administrative job, but you have a lot of work that comes with that, but it's something I enjoy a lot because it forced me to think about things that are important, not technically, but in general about research, right? And one of the things that really concerns me, and you may have heard about this, is the issue of quantity versus quality, right? The pendulum, right? How things are in research, more research or better research, right? And of course, this has happened forever, right? But I think, this quality over versus quantity, this pendulum several decades ago was more on the quality side, right? I have been around, doing research for several years, and I would say maybe even before I was doing research, it was clearly on the quality side. Different reasons, right? Maybe one is globalization and the internet, right? It has trying to have made that quantity, the pendulum move to the quantity side, right? And I think that's really what we are today. To the point that I think it has become really a wave, a really crashing wave on the quantity side. Okay, we may discuss that, but there are many factors that why that happened. But the signs are clear there. I mean, this year, we are seeing for many of the top conferences submissions duplicate. Okay, not just increase a little bit, but twice as many submissions to many of the top conferences. Okay. And so me as a PhD director teaching students about research, I need to admit that in their professional life, at least that's how it is today, not that how I like it, but I have to admit that when they go out there as a researcher, they will have to live in this environment where, and they have to strive where quantity is now where the pendulum is, right? So how I approach that tough life, right? Well, a couple of ways. First, I talked to the students about, well, two things. First, we need to recognize that the real world, I mean, of course, everybody will tell you very quickly why it is more important quality over quantity. The reasons are obvious why quality has to be over quantity. But the reality of life is that there's a lot of pressures on research to prioritize quantity over quality. Many reasons why, which are not good, but they're there. So I tell this a metaphor to the students, so they start to think about this, right? I mean, we all want to do research that is impactful, that really makes a difference in our world, right? And I tell them, well, we all know this metaphor about research as stepping stones, right? I mean, each research work that we do is a stepping stone to advanced knowledge, right? And I said, well, okay, so high quality, high impact research is like this stepping stone in the form of a large stone slab, right? And by contrast to that, well, low quality research will look like a pebble, right? Something much smaller, right? So in our path of research, if we get to the point where now we are in a gap, right? A knowledge gap that we need to bridge, and that gap, I mean, in this metaphor is a rapid running river. Well, how are we going to bridge that gap? Are we going to bridge that gap by putting thousands of pebbles one on top of the other? I don't think that's going to work, right? I mean, it gives that maybe the feeling that we are making progress because we see the volume, but we are not really bridging that gap. That gap, it can only be bridged with big, slabs, right? So that's one of the things I mentioned to the students. Think about this. I ask many times to my students, think about this, okay? Because at the end of the day, that's what we are PhDs for, right? To think, right? So that's one thing. The other thing I tell them is this another image, right? I tell them, well, think of yourself as a surfer, okay? Think yourself as a surfer. So do you want to be, caught in that wave of quantity over quality, right? In a way that you cannot control what is happening, and the wave takes you tumbling over, to the shore, right? And of course you don't want to do that. What I tell them is, well, you want to be that expert surfer, right? That with quality moves, you get to surf that wave, right? I mean, again, acknowledging that the wave is going to be there, but I really push my students to think, how is that I can be that quality surfer that can navigate the wave, right? I mean, I'm going to be doing quantity work, but it has to be with that gracious of the quality, right? And so how we do that? I mean, of course, talking a lot with the students, but also recognizing that this expert side is that they need to know the surfing techniques, the research techniques, right? And how they are going to be using them. How do we get a balance on the surfing board, right? And so where I do that is in our class that we have on research methods, right? So this is a very particular course. It's not your typical course that for research methods where you teach students how you write a technical paper, right? We have that, okay? We have a course like that, but this is another course that is this course, where I ask the students to think about what they are doing and to think of what you are doing when doing research. So we cover a range of topics that really goes into that, knowing what is happening with research. Right? One is the dovetail of critical and creative thinking. If you read the paper, you start to recognize, knowing this, you start to recognize how you are intermixing critical thinking with creative thinking, what I call informed creative thinking, right? We talk about inductive and deductive reasoning, argumentation, formal logic, also formal methods is what's called, or deductive system, but also we talk about fallacies. A big part also I emphasize abstraction is a very powerful tool. Abstraction is even more powerful when you understand what is happening with an abstraction. Assumptions and trade-offs. Of course, it will take me, it's a full course this, but I wanted just to share with you the notes are online, and if the link is there. If you want to QR code them, you can also get the notes for this course and just read. I mean, read them, enjoy them. Have fun. I mean, if my idea in writing this is notes from a course from someone that loves research to others, trying the others also to learn to love research. Okay, and I think that's pretty much it. Thank you, and we can have more questions if you want. Yeah.
Thank you, Professor, for accepting our request and delivering an interesting talk, and for the bonus part. Are there more questions from the audience?
By the way, I'm so proud of myself. I finished right on time. I mean, 5:00. Yes.
So what was the time dynamics that was simulated? Was it IID block fading, or
Which one?
was it IID block fading that you simulated for the primary and the secondary users?
You mean the channel?
Yeah.
No, it's actually it's a pedestrian B channel, so there is some correlation. Yes.
So I'm curious about why the weights became similar when they got closer. So my main question is, what can we tell about the loss function that the training on it from different points resulted in the same minima?
I don't think it has to do with the loss function. It has to do with what are the weights. The weights are representing the environment, and essentially is the encoding of the Q values, essentially, right?
But it's optimizing some function.
Right, but what is looking at is essentially is a representation of the environment from the perspective of the interference. So for one cognitive radio, what is the interference it is feeling, the noise that is feeling, what is the power it can put out without interfering too much or interfering too much to the primary network, right? So it's all these representations of the wireless environment, right? So that is for one cognitive radio. And it is represented, it is encoded in those weights. Now, the same happens with another cognitive radio, right, that is nearby or at some distance. What happens is that these weights are similar or correlated, but not fully correlated, right? So they are not identical. So why is that? It's because if you think of, if you try to feel the environment, right, the wireless environment, is that one cognitive radio will be feeling, no background noise, interference, and the other that is nearby may be feeling the same sources of interference, the same noise, but because it's a little bit separate, it has similar power, but it's not exactly the same. And of course, there may be their own local, more local type of variations, right? That happens because there may be another transmitter and so on. The point is that you can ideally separate this representation of environment between something that is more general, right, versus what is more localized, right? And that is where that cross correlation comes from. The cross correlation is what is similar to the two, and then not cross correlation is what is the specific differences, the nuisance local wise. Okay, and of course you know how wireless work, right? I mean, distances tend to decrease logarithmic, right, with different power, right, but exponentially, sorry, with different power, right. So the more distant apart they are, the more different. That element that is common to them is going to become smaller and smaller compared to what is the local one, right? So that is really what I think happens there. It's not so much about the loss function, because the loss function is just trying to estimate, right? It's the estimate of the weights, okay?
So, but even if they are in the same environment, let's just say I start two parallel networks, and write one top of the other, but they just had different initializations.
Yes.
It's really not, especially when the networks are over parameterized. If I have a lot more layers, hidden neurons, it's not always clear that they would converge to the same value unless the loss function is very special.
Right, and here they're not converging to the same value, okay?
But there is a very strong correlation.
Yeah, but that's the thing, it's a correlation, right? And it doesn't need to be, it's not the same values, right? I mean, you have correlation equal to 1. Is there a scale? 1 is the scale of the other, right? They don't need to be the same, right? So yeah, we are not saying that they are the same, nothing like that. Is that they are, and as far as we can see, because I mean, there's a lot of questions still there, but as far as it goes in terms of the encoding of what is being represented, there is the cross correlation is telling us there is an element in common. That's as far as I mean, all what we are saying there, you know. And I mean, that element of common is what is common in terms of the wireless environment, right? I mean, like here, I mean, if we think of the wireless environment about sound, right? There is a dominant sound of me talking to you, but we both can hear pretty much similarly, you know, the noise coming from outside, right? That is a common one, while what I'm doing with you is the local one, right?
Just a quick question. So you used only the last layer for and there was quite a bit of correlation there. So you used that layer. The lack of correlation in the early layers, is it because of the over parameterization?
It may be that, or I mean, it has to do also with random initialization, because each of these were completely random initialized, right? And it may be in the sense that the earlier layers, of course, have less abstraction, right? And the process here is that representations when we get to the most abstracted level of representation, that is when things start to click, right, in a sense. That's really what we are seeing there. Yeah. Right.
Thanks again, Professor.
Thank you.
Thank you.